When you look at the output of a modern AI, you are seeing the results of sophisticated numerical logic. It produces photorealistic faces, vivid landscapes, and poetry that mimics human emotion. But beneath the surface, there is no imagination. There are only zeros and ones. It is easy to assume there is a spark of genuine comprehension inside the box. You ask a question, and it gives you a thoughtful answer. It feels like someone is home. However, a machine has no biological brain. It cannot experience the concept of beauty, the sting of sadness, or the rhythm of a poem. It processes electrical signals and numerical values according to strict rules. To understand how these systems actually function, we have to look past the myth of a digital mind. What remains is a meticulously stacked structure of mathematical operations. If we start from first principles, the reality is based on organization. Machines don't understand meaning, they understand structure. This diagram lists the specific mathematical steps required to build this structure. It begins with numbers, scales up to vectors and matrices, incorporates probability, and culminates in optimization. Artificial intelligence is an emergent property. It appears when we climb these specific mathematical steps in a precise order, turning raw data into recognizable patterns. The first problem is storage. How does a machine record the meaning of a word or an image without knowing what it is? The solution is the vector. A vector is an ordered list of numbers. You can think of it as a compass that gives data a specific direction in a digital space. This graph shows vectors plotted as numbers with direction. If you have a movie, you can take its measurable traits, like its level of action or romance, and convert them into exact numerical coordinates on an axis. Once ideas are converted into coordinates, machines can compare them. They do this by measuring the geometric distance and alignment between those points in space. We measure that alignment using the dot product. As you can see by the angle between these arrows, when two data points face in roughly the same direction, the mathematical score is high. Geometric closeness equals conceptual similarity. To an artificial intelligence, the difference between king and queen is literally just the physical distance between their coordinates in a geometric space. Comparing two concepts is simple, but real-world models must process millions of these vectors simultaneously. This requires a matrix. In AI, matrices are not just tables of numbers. They act as machines that transform information by reshaping the space where data lives. When a matrix multiplies with a vector space, it stretches and rotates that entire grid. By warping the geometry, it pulls overlapping data points apart and separates them into distinct categories. By repeating these transformations across multiple layers, the system isolates increasingly complex features. Early layers use this geometric reshaping to find simple edges in pixels, while later layers combine those edges into the shapes that eventually form a recognizable face. But what happens when the matrix transformation makes a mistake and misidentifies a piece of data? Neural networks handle this through a feedback loop. When they get an answer wrong, they calculate the loss, the exact mathematical size of the mistake. The system uses optimization to find the lowest point in a topographical error landscape. Finding the bottom of this valley means the error has been minimized as much as possible. Gradients act as the compass for this journey. They point out the steepest way down, guiding the network step by step to the bottom of the slope until the prediction is accurate. This process of minimizing error over millions of repetitions is what we call machine learning. It is a strictly mathematical pursuit of accuracy. This textbook page outlines the full mathematical architecture. AI is the continuous loop of measuring data, transforming its representation, and correcting errors through optimization. The systems we converse with daily are performing billions of these silent mathematical calculations every second. This architecture raises a question for the future. How much of what we call human intelligence is actually just the sophisticated processing of patterns? Centuries of human mathematics have been layered together to create these systems. By stacking simple rules into a complex architecture, we have built a mechanism capable of generating increasingly useful judgments about the world.